Today we're going to talk about periodic trends or periodicity. Sounds like a made-up word. We can have trends that go up and down groups, and we can have trends that go left and right across periods. We have general trends, and then of course it's chemistry, so we have exceptions to those. So in general, they go the way that this chart shows. Uh, for this particular video, I'm going to discuss atomic radius because everything else is based off of the atomic radius and why it gets bigger and why it gets smaller. The arrows point in the direction in which whatever it is they're talking about is getting bigger. So going down a group, right, the radius is going to get bigger. Going from right to left, radius gets bigger. We're actually going to discuss why radius gets smaller going from left to right. And then the other two, plus we would add electronegativity, all get bigger going to the right and all get bigger going up. So let's start off with atomic radius and discuss why it goes in the direction that it does. Here we have kind of a middle school looking magnets, and everything in the atom and everything in chemistry is based off of opposites attract and like charges repel. In the atom, we have two particles that are charged. We have the electron, which is a -1, and we have the proton, which is a +1. Well, if we are a +1 here and a -1 here, they're going to attract. So the protons and the electrons attract each other. If we had a proton here and a proton here, they would repel. However, what we're going to be talking about, it would be a negative electron and another negative electron, and they're going to repel. So we're going to have proton electron attraction, and we're going to have electron repulsion, and they're going to push each other away. So all the concepts we talk about are based on that. We'll get the complicated one out of the way first, and that is when you're going from left to right across a period, the atoms get smaller. First of all, that's counterintuitive because if you look at the periodic table, masses increase, so you would naturally think that the atom would increase. However, the space that's going to be increasing or decreasing is going to be empty space that the electrons travel in. So we're not talking about compressing mass and therefore the bigger mass must be bigger. It's the massive empty area that the electrons travel in. So if the electrons are overall are more attracted to the nucleus, they're going to start getting smaller and smaller. If the electrons repel more, they'll end up getting bigger and bigger, and that's what dictates size of the atom. So going into it, we have lithium, beryllium, boron, carbon, etc. We keep going, but we want to look at the electrons compared to the protons here. You can see here that the lithium has an atomic number of 3, beryllium 4, boron 5, and carbon 6, etc. And it's going from left to right. So this is the part of the periodic table we're referring to. Lithium's going to have 3 protons because it's got the atomic number of 3. So that's 3 pluses, and then it's going to have 3 electrons because they're going to be equal. These are uncharged atoms, and therefore 3 pluses, 3 minuses. The pluses are all in the nucleus. That's a single 3 plus charge, whereas the -3 are several negatives spread out here. We're talking about the second energy level where this electron is. And if we're playing God and we got our little kind of Lego set of protons, neutrons, electrons, to go from lithium to beryllium, we would add 1 more proton and we'd add 1 more electron. And as we go across, we add 1 more proton, 1 more electron, 1 more proton, and 1 more electron. So that's how it goes going across. Now, adding protons to the nucleus adds to the nuclear attraction. Z for carbon equals 6. Z for boron equals to 5. However, if your argument is that it gets smaller going to the right because you're adding more protons. That is correct. However, we are adding more electrons as well, and you can't discard that, and you can't just not talk about it. So adding protons should make the atom smaller. So you had 4, and that's a 4 plus, so it pulls these electrons in tighter, right? They pulls them in tighter. They have a smaller radius, and therefore the atom is smaller. However, adding more electrons, if we just said we had 4 electrons, that means we have one more electron-electron repulsion. Electron-electron repulsion pushes the electrons out and makes the atom bigger. So the protons make it smaller, the electrons make it bigger. Adding one more of each, all things being equal, should be a wash, should be equal. And if you went across the period, you have 4, 4, 5, 5, 6, 6, and essentially adding an attraction and adding an equal repulsion should mean the size stays the same. However, it does get smaller. And the reason why it gets smaller is because we're adding electrons to the valence. Adding electrons to the valence still has a repulsive part to it, but it doesn't repel as much as would be for the core electrons. It's kind of like if you're repelling, this electron would be repelling in all directions, and therefore how many electrons are actually on the outside of it in order to push it out farther? And the answer is not very many. If you're pushing electrons in, that actually doesn't make this outer electron any smaller radius, it actually makes it a bigger radius. So I know it's hard for people to comprehend this, but adding valence electrons is not as large of a repulsion as adding the protons to the nucleus. Therefore, we have this thing called Z effective. Z effective, this is like a subscript for Z. Z is the nuclear charge. Z effective is the actual attraction to the nucleus, and therefore, as it goes from left to right, Z effective increases, and the size of the atom actually decreases. If we are going down a group, like we're going from lithium to sodium to potassium, going down a group, the radius gets larger, so the atom gets larger. And the reason is really simple, there's more energy levels. The same issue with going from left to right. As we go down, we add more protons, we add equally more electrons. So if you go from lithium to sodium, you add 8 protons and 8 electrons. Sodium, potassium, 8 more protons, 8 more electrons. So it's kind of a wash with that, but because of the way that quantum mechanics works, those electrons end up popping up to an upper energy level, so you kind of have more peels around the onion. The explanation is really simple. All you have to say is if you're going down a group, the radius gets bigger because you have more energy levels, and therefore the valence electron is farther away from the nucleus. This is going to be really important in discussing why ionization energy, electronegativity, and electron affinity all decrease as the atomic radius increases. Now let's talk about the radius of ions of like atoms. So here's a sodium, and here's a sodium plus. Well, they're showing here in this picture that in order for it to be a plus, you have to lose an electron, and that electron comes from the third energy level, which is now vacant, as they say, it's empty. So the sodium atom has 3 energy levels, and the sodium ion has 2 energy levels. So that alone is enough to make the ion smaller. We're going to talk about it in terms of number of protons and electrons because we don't always lose an energy level. When we talk about anions, that's not what happens. So the sodium has 11 protons and 11 electrons, and the sodium ion has 11 protons and 10 electrons. So the attraction to the ion and to the atom is the same. However, the repulsion is not the same. the repulsion for the atom is more, and therefore it's a larger atom, a larger radius. Now, in this case, again, probably the proper explanation would be it has a third energy level, where sodium ion has only a second energy level. If we're looking at IB and how they want these things to be stated, if you can say that the sodium ion has one less energy level, or you can say it only has energy levels up to 2, the 2 energy level is a more specific answer, and that's what they're looking for. Now we're going to look at the chlorine atom versus the chloride ion. The chlorine atom is going to have 17 protons and 17 electrons, whereas the chloride ion also has 17 protons because it's still chlorine, but it's going to have 18 electrons to become charged. So back to what we stated earlier, this one doesn't have more energy levels. You're adding that extra one to the third energy level. It actually fills the valence, which is why it's stable. However, it's got 17 positives and 17 positives. That means the attraction to the nucleus, the actual attractive force, is the same. That's Z. That's a pretty sad looking Z. Let's try that again. That is Z. However, the repulsion is going to be 17 for this one and 18 for this one. One more electron repelling. One more electron repelling means that this atom is going to have a larger radius because the electron repulsion is greater. Since the positives pull and the negatives repel, it's like opposites. So they try to get bigger or smaller. Since the attractive force is the same, the repelling force is bigger for the chloride. Z effective is actually smaller for the chloride, and Z effective is larger for the chlorine, which is why the chlorine is smaller. The measured attraction is greater. Type of thing, and we are done. Here on the left, we have a phosphide ion, and on the right, we have a chloride ion. The phosphorus is going to have protons of 15, so that's a single 15 nuclear charge. The chloride will have a plus 17, more protons. However, the reason why phosphorus is a 3 minus in the ion and chlorine is a 1 minus is because it fulfills octet rule. So the electrons that they're going to have are going to be 18 negatives, and the electrons over here are going to be 18 negatives. So on the surface, phosphide 3 minus and chloride 1 minus aren't related, but they are related. If you look at the actual protons and electrons, these are the items that make atoms bigger and smaller. You can see that the repulsive force for both of these is identical. Same electron-electron repulsion, also same shielding effect. So that would be equal. However, for the chloride, the nuclear charge is a plus 17. And then for the phosphide, it's only a plus 15, which means the chloride will have a much greater attraction, so it pulls the electrons in, whereas this one has less of an attraction, it doesn't pull it in as much. So the phosphide will be a bigger ion than the chloride because of attractive force to the nucleus. So these aren't the same trending left to right because these are ions. The trending left to right we talked about earlier are for atoms, or in other words, uncharged atoms, not the ions. On ions, you got to separate them in itself. The fact that these things have the same number of electrons means these are isoelectronic species. The more protons, the smaller, because the attraction is greater. You can have a potassium plus, and while it's got a fourth energy level, it doesn't anymore because it lost it. It still has the same electron configuration and looks the same. So the explanation for why potassium plus is smaller than the chloride has nothing to do with energy levels. It has to do with more attractive force to the nucleus because of more protons. The electrons are actually the same because they're isoelectronic. I hope this video helped. We'll talk to you later.